So entropy, which is abbreviated with a capital S, is a thermodynamic function that increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. When you read this, you're like, what the heck kind of a definition is this? Is this in English? What the heck do you mean by saying we want to increase the number of energetically equivalent ways to arrange a particular state? Doesn't make the most logical sense, so let's kind of come up with a couple examples here. There was a chemist slash physicist slash scientist by the name of Ludwig Boltzmann, and in the 1870s he came up with a mathematical expression for entropy. He said entropy, capital S, is equal to a constant K times the natural log of W. S in this equation is the entropy. The K constant is our gas constant R divided by Avogadro's number. It's not really important about the number, but the units are definitely important, and this is in joules per Kelvin. And this term, the ln of W, is unitless. And to really understand this definition about entropy is we need to know what W is. And W is going to represent the number of equivalent ways that we can arrange particles in a system that have the same energy. So how do we take these words right here and make sense with what goes on at a molecular level? So what I want you guys to do is to consider a fixed amount and when we say fixed amount, we're saying n is constant of an ideal gas. And we're going to consider a fixed amount of an ideal gas at constant temperature, pressure, and volume. So if we consider this, we have an ideal gas with these elastic conditions, and if we fix all these properties and make them constant, our energy is going to be constant. So what we can look at is a constant energy system. If we have 10 particles, they're going to have one energy. If we have 5 particles, they're going to have a different energy. But each of those systems are going to be constant. What is not constant is how those molecules are going to move around within the system. So if we take a look at one of these little PhET simulations that we have access to, and if you Google PhET, P-H-E-T, simulation, and put in reactions and rates, you can actually have access to play around with this particular tutorial. So let's just say I have a molecule in a system. And if there's only one molecule, it's going to be moving at one speed. We can assume that the speed of this molecule right here is going to be proportional to its energy. So if we fix this ideal gas at a constant pressure, a constant volume, constant temperature, and we keep one number of moles, we're going to have a constant energy system. So you kind of picture this gas molecule moving around and bumping around here in this container. On a scale of 1 to 10, and you don't have to say this out loud, but think in your mind about how fast this is moving. Say it's about a 4, right? So if this is moving at a speed of about 4, the energy is going to be roughly 4. Okay? It's easy to keep track of. We got one particle in there. It's moving around at a particular speed. We can bump in another particle here, so both of them initially are moving at a speed of 4, right? So our overall average energy is going to be the sum of these energies, 4 plus 4, divided by 2. But watch what happens when they bump into each other. One particle is now moving faster, and another is moving slower. So let's just say one's moving at a speed of about 6, others moving at a speed of 2. We can keep track of those fairly easily. Okay? What happens now if I increase the number of particles? I want everybody to keep track of the speed of each of these particles at any given moment. So if I would hit pause, you could tell me exactly the speed that they're moving. Okay? This is kind of how entropy works, where it's easy to keep track of things if there's only quite a few. And even though they're clanking together here, you can kind of get a glimpse of what the speed is. Now, every particle I put in this box, I want you to keep track of. So tell me at any given moment what the speed of every single molecule in this box is. So now I have 30 of them in here. And if I hit pause, can you tell me right away what the speed is? Everybody kind of laughs because they're like, oh man, you're crazy. Everything's going around like this. I'm putting 30 particles in this particular box here. Now think of this in the perspective, right? If I have a mole of those particles, there's 6.022 times 10 to the 23rd of them. And think about your body. How many molecules and how many particles are involved in your body? In one strand of DNA, in anything like that. What nature is going to do is nature is going to favor these disordered systems, or systems of high entropy. So if we can predict if a process is spontaneous or non-spontaneous, it's going to relate down to the entropy of our particular system. If you think of a lot of diseases that result, something like cancer, it's from mutations that happen inside your body that your immune system can't combat. So we have this entropy happening in this more disordered type of a system because there's so many things to keep track of. So when you think about entropy and states of randomness and disorder, the more particles that you have in this particular box, the more it is to keep track of them, or to keep track of a well-ordered system. Because all of these things are moving around here, and they're going to give us an average energy. But each individual particle is moving at a different speed, and there's a lot to keep track of there. So what we can say then about this is all the individual particles are considered to be what we would call microstates of the entire state. And they can sum together we can try to keep track of certain things. If we change this back to 2 particles, we can easily keep track of the energy here. And we can make assumptions based on what restrictions we can make and look at the various states that could arise from this.